Yeah, Yuri, please.
All right. I'm pleased to see you. I wish to thank organizers for the opportunity to give such a talk. Eventually, I always wanted to give talks in Delft at my class, but it appeared to be that these opportunities are very rare. I just counted for 25 full years I've been in Delft. I talked only 5 times. Very good. What do I want to do? I want you to outline my vision. That would be vision not to a certain layer of physics, but rather to methods of physics. I'd rather talk about vision on theory. What is a theorist, and what should one do if you're a theorist? It's meant to be personal. You don't have to agree with me, but I would try to motivate you a bit. Why do I come to such vision? Right, sir. I will talk about theory and misconceptions of theory. I will talk about the vision, and that will be formulated at a rather abstract level. And in order not to be too abstract, too theoretical, I would just give straight concrete examples, times allowed. That concerns recent publication. I hope to talk about recent preprint, but as usual, as preprints, we need yet a couple of days to put it on ConMat. Sorry about this. And stuff we have recently finished and are going to write up. Okay, that's outline. Now let me start perhaps with my roots. How I became a theorist, how I became a theoretical physicist. Well, I've been following an education which brought me there. That education had many facets as any university education, so it contained also a substantial part of military training. All right, and a part of military training was very specific, but absolutely necessary. It is a training of what in English is called goose step, right? Sometimes you see the videos of soldiers which walk really in a strange manner, and that from a military point of view is considered to be beautiful. Good. So there was a certain officer or major which wanted to train us in this goose step. Of course, it's very practical. You really have to do this. Okay, we've been trying to do this, the whole platoon of students, physicists, and he was not satisfied with the results at all. He was furious several times, but kind of calmed himself, and he uttered a phrase which shocked me by the time deeply. He said, "You're hopeless. Let us do some theory." Good. That time I recognized that there is a quite established theory of goose step. Of course, as many theories around, it's very applied. So that's a theory how high should you press your foot, at which distance. Well, that also has some physical meaning, kinematics of human body, perhaps even nonlinear synchronization. So there was quite some theory. I was going to become a theorist by that time, and I was shocked to see such a vision. And this vision on theory is quite widespread, just some dead knowledge, which is stored somewhere. And which has to be applied, has to be invoked anytime there are difficulties on practical side. Right, I recognize that I certainly do not want to do theory of goose step. But even by that time, still deep in 20th century, there are also examples of more interesting theories. And people had a notion that theory should fascinate, should predict something, and perhaps should be useful, should lead to something. Right, here I put pictures of two theories which have been popular in 20th century. Right, both theories were quite fascinating. Both theories have had impact. Right, so one theory actually was correct and confirmed to experimental data. There was much experimenting upon another theory, and I guess the final conclusion that it doesn't fit anything, and also internally contradictory. But guess who from these two theories got most citations and most public attention? I hope you can make your mind itself. So that was my background, which kind of shaped me to some extent, which gave me a notion what I like and what I'd like to do also in theory. Since that, many years have passed, up to about 40, so my career, which was just to start by that time, is more or less rounded. And that major, well, must be not around for a long time. But from time to time, I have a feeling that he's alive and I meet him again. For instance, there is, as you see, a job advertisement, sorry. Actually, I've promised to propagate it, so I use this opportunity to propagate it to you. Our friends in Nijmegen look to feel an opening for a series. But for me to read this, I fully respect my colleagues, and I fully respect the difficulties of actually doing job search of any kind. Still, I was shocked, and as in the case with Major, also provoked some thoughts. Let me explain what I find shocking, or at least not corresponding to my vision. First of all, it was about theory, and it also imposed some constraints, which frankly do not look consistent to me. Let me give an example. Once, well, many years ago, I was in the splendid city of Berlin for the first time. Eventually, with a second speaker, with Harry van der Zand. Right, and it happened so that I got to police station. I wouldn't explain why, but I had to spend some time on a Berlin police station. And there I saw a job advertisement recruiting Berlin Corps, which I kind of also remember till the end of my life. To put it shortly, it said, the applications of all nationalities and ethnic backgrounds are cordially welcome to Berlin Police. but a successful candidate must be blonde. Yeah, I hope you now understand what kind of constraint, contradictory constraint I mean. Good. What else which I don't quite understand in this advertisement? Inspiration. For me, theory, it's kind of very special field, if very special activity, if one does it correctly. An activity which mostly should have some inner inspiration, perhaps emotional inspiration. It's while neuro data, I see it rather as tools to do this activity. So it would be, for me, it would be like, say, advertisement of a car-inspired theory, or whatever, Hammer-inspired theory. I guess there's some contradiction between tools and goals. Right. So, thoughtful of this kind, I decided to make my own job advertisement for a series. Let's go quickly for this. First of all, what should be filled? If I put excessive constraints, if I'm free to do this, I would say it has to be full of a whole universe, or whatever blank sheet of paper, which you can fill with formulas, which could concern anything. Has to be total freedom in the field. Method must be scientific. Theories must be good, correct. Otherwise, they have no value. It's just fantasies. What scientific method? One can argue about this. Perhaps I don't want to. Mathematics is science, physics is science, medicine. Most people would say it's science. Then homeopathy is science, astrology. It's quite developed science. Anyway, let's stop here. What's important to me is the mood with which you do these activities. And I guess it would be very important in my advertisement. This mood kind of it's rather a complex emotional state. So I need to use kind of special terms which come from other languages. Perhaps you have heard of this, but yeah, let me shortly explain what I mean. Saudade, it's Portuguese or Galician, whatever you prefer. That means greatest strange thing. It means sorrow, which you get from an attempt, from desire to reach something which you cannot. But sorrow is so intense and unreachable, is so unreachable that this emotion is positive. So data is not nostalgia, whatever. It's not what kind of most Europeans think of it. It's strong, positive emotion. Similar emotion, similar emotional state comes from Japanese, from venerating cherry blossom, hanami, and it's called mono no avare. I believe it's correct pronunciation, didn't check it. What is this? It is a feeling that beauty is untouchable, cannot be conceived, that everything in this world will perish, us and everything around it. But if you do it correctly, and Japanese usually drink a lot during hanami, then this emotion also becomes positive. It kind of drives you. It kind of makes you strong. And I believe that real theories should, at least from time to time, be guided by these emotions, by internal beauty of theoretical physics, by the fact that most theoretical problems you cannot solve, cannot fully understand. Nevertheless, one should go for it. Fine. Goals. What would be goal to theory? The goal of good step theory is pretty obvious. What would be a goal of new theory? Of course, theory should provide some answer, should provide some prediction, but not every answer. It should provide answers which would provoke, which would cause other questions. Otherwise, it's also, if you ask me, doesn't make much sense. Because if you look for answers, you know for what answers you look, and then it modifies the whole setup. Fine. I'm already out of time. Let me just formulate the vision very shortly. So the vision won't be about certain field of research. The vision would be about methods of theoretical physics, or whatever, any theoretical activity. First of all, theoretical research must be correct. Second, it should not bore, otherwise it also doesn't make sense. It has to be novel. It's not, there are two concepts of novelty. I would invoke the concept of numerical minimization. If you think about numerical minimization, first idea is that you should go downhill, always downhill. And that would be the most, the best strategy. But if you kind of ever look at numerical minimization, the numerical minimization, you understand that don't do this. In numerical optimization, programs always take side steps, try to go to orthogonal direction. And this is eventually an optimal strategy. And I believe theoretical researchers should also go along this line. It's better to be simple, otherwise nobody understands it. It would have no impact, no significance at all. Again, it must give an answer, but that answer would rather provoke some other questions. And ideally, the research is not repetitive, like the same idea is put everywhere, and there is a whole line and bunch of papers. Yeah, I don't think it's a proper way. Good. That is the idea, that's the vision. There is implementation of this vision. And this implementation of this vision finally brought me to a certain field, which I don't like to some extent. I would love to be a universal theorist, in fact. But anyway, it has to be quantum because it's not boring. It's always fascinating. It has to be devices because it has to be simple, has to be novel, and superconductivity because superconductivity still remains kind of magical property of this world, still fascinates us in many topics. So there is vision and strategy. There are many disadvantages in this strategy, but I don't want to talk about this now. If you have questions about this, please be welcome. Very good. In remaining minutes, let me quickly outline my the last achievements of my group, and let me try to put it into the scheme. Right. Recent publication. It's polarization of non-equilibrium quasi-particles in superconductors. People who are dealing with superconducting qubits know that these quasi-particles, non-equilibrium quasi-particles, frequently make a nuisance to the work of superconducting devices. So what's going on? So this quasi-particles come from somewhere at high energy, they're low energy, they get somewhere at the gap edge. All right, suppose we have some quasi-particles over there, let's consider another one, incoming quasi-particle. Good. The quasi-particles can change only due to annihilation. Two quasi-particles come together and they emit a photon. And for this, they should have opposite spin. Good. So if I look at this cartoon, the quasi-particle is opposite spin, kills a quasi-particle which is already present. Yeah. If it has the same spin, if it cannot find a quantum partner, well, it just lands. So in this case, we have minus one quasi-particle. One quasi-particle is killed. Here we have plus one. So it looks like we don't have any net growth of the number of quasi-particles. However, if we do it quantum mechanically, this is very simple quantum mechanics. It's about spin states of cluster with n spins. So now this number becomes important. It appears to be that polarized clusters grow when they're fed up by unpolarized quasi-particles. And upon spin conservation, this process cannot be stopped. The cluster would go randomly, become bigger and bigger. If you take into account spin orbit effects, spin conservation, which break spin conservation. In fact, there are relativistic effects, as you know from spin orbit theory. Good, one has this marvelous estimation. The full number, or the possible total number of spin in this cluster should be of the order of fine structure constant to the power -2. That's a big number. It's like 10 to the 4. Good. We kind of make more sophisticated theory, how to estimate the polarization. It depends on spin flip time. It depends on all spin non-constant effects. It's not very important. Most important is to get to practice how one can see the spin of these quasi-particles. It's not that evident. They're somewhere deep in superconductor. So that's how we get back to the field of quantum devices. And I guess it was also essential part of our theoretical work to invent this simpler device. So what do? We have a trap for these quasi-particles. We feed this trap with normal lead. In a way, we can apply voltage, we got more, or we can get less quasi-particles. And with a squeeze loop nearby, we measure magnetic field produced by their spins. This field fluctuates because polarization is dynamical. New quasi-particles come and go. If spin is large, as we predict, the noise becomes also enhanced. Kind of roughly, the noise is proportional to the number of particles which correlate their spins. All right, that's a concrete scheme how to look at it. Let's see. Oh, I still have some time, so let's move to the second example. It's about, it's mostly about QTF, sorry about this. It's mostly about topological quantum computation, which is in its kind of dogmatic form, in traditional form, is based on the idea of binding, or in other words, on exchanging anyons, exchange statistics. And in this case, one can manipulate quantum state without making any decoherence, without making any memory loss. It was very attractive concept. As you know, it's one of the kind of pillars of QTEX. They try to achieve topological computation in on the basis of superconducting nanowires, semiconducting nanowires brought together with superconductors. Well, an obstacle is that these wires are one-dimensional and one cannot write in one dimension. Good. One could, of course, think rather obviously one can make a kind of a network of these wires. This network can be whatever two-dimensional, one can bury it in there. But we try to go a little bit orthogonal. And we propose to make a little compromise. Let us invert yet another excited state in this number. So here we have Majorana modes, anyons. And let us do what is kind of usually done in any quantum manipulation. Let's do a resonant manipulation. So in fact, we were able to show that with this compromise, one can easily write these anyons. Moreover, one could do any unitary operation, not only writing, which is prescribed by topological computation dogma. And right, if one also measures occupation of this excited state, one can also measure in this topological subspace, one can also initialize wave functions in this topological subspace, which is very difficult in topological computational skills. All right, so it is a bit technical. The idea is not theoretically involved, but it's orthogonal. That's why I think it is useful. Okay, so some more details we kind of simulate engineers, I would say. So here it's a concrete device with gates, and we really compute amplitudes of the voltage modulations to these gates, which would lead to a certain braiding of these Majoranas. Let's see what I'm doing with respect to time. I think we started a bit later, so I have a couple of minutes. Let me talk about third project. It's about Weyl points, but in very unusual setup. Let us talk about semi-classical superconducting structure. There are Andreev bound states, and they have continuous spectrum. There are recent predictions, recent activities that this means that at certain phase settings, the superconducting structure becomes gapless superconductor, kind of a metal. So very many levels and F levels come close to zero energy. And our idea that in this regime, one can see very many Weyl points if one takes care to resolve this dense spectrum into individual levels. Okay, Weyl point, what's the Weyl point? It's something that requires 3 parameters, and for us it means that we need to work with 4 terminal structure. It's a conical singularity in a spectrum, which also bears topological charge. This work is mostly numerical. So it's an example of positions of Weyl points of 2 different charges. Topological charge comes with plus minus 1 in a 3-dimensional brilliant zone of 3 phases. Fine. So that work was planned as purely illustrative, just to get an answer about statistical properties of Weyl points, just to give answers how many are there, what is the density of these points. what's the correlation between bonds? Tools which have to be applied is a very established tool of random matrix theory in combination with semi-classical quantum circuit theory. But we get some answers. For instance, for a structure made of quantum point contacts, the number of Weyl points is certain coefficient, which took months to compute. Nevertheless, we got it. And well, conductance of the structure to a certain power. We didn't expect any surprises, and not much novelty, but we got one. When we analyze correlations of Weyl points, we understand that the screening of topological charges is very weak, surprisingly weak, which indicates some, well, I dare to say so, internal contradictions in random matrix theory. So now we are in a quite abstract research exploring this anomalous experiment. Very good. With these examples, I hope I could illustrate my vision. So thank you very much for your attention.
Thank you, Yuli. We can take a few questions. So please, if you want to ask a question, please raise your hand in Zoom. And people are thinking, oh yeah, okay, Bas.
Thank you for a very interesting talk. I actually had a question about the beginning. Your example in the Berlin police station, they were trying to hire blonde policemen, which is strange because why would a blonde policeman be better than any other, right? That is your, that's why you find it strange.
I don't find it strange. I guess they perfectly explain what they want. But if you welcome the members of all races and ethnical backgrounds and simultaneously expecting that they're blonde, I find it rather contradictory.
It struck me as a little bit contradictory with your ideal candidate for your job position, which had to operate in a certain mood. I mean, what if you're just an angry theorist who always operates in a very angry fashion, always writing down his theory, just wanting to get to the answer?
I took the policy of previous advertisement. I decided to put that many constraints, which I want.
Okay. Yeah.
I found this constraint important. I don't think that angry theorist would do much, but of course I would allow him or her to be angry at working class.
Thanks.
Okay, thank you. Do we have more questions? Really, then I will ask a question and then probably we will go to Harry after that. At some point you mentioned, I mean, you had this criteria, and one of these criteria was that research has to be novel. Could you define novel? Because I guess if I ask different people, they would have different definitions. And some people would say, okay, if the idea was ever published by somebody in a completely different field, that's already not novel.
You're right, but perhaps there's no absolute criteria of novelty. Since it's a vision which is kind of practical, which gives you motivation, I think first of all, you should have a feeling for yourself that this is novel. So at least for you, it has to be novel.
Okay.
That would be the minimum requirement.
Great, thank you. Unless we have urgent last-minute questions.